Hello everyone. So, this is lecture 1 for this next module, module number 5. In today's lecture, I am going to talk about the internal memory. So far we have discussed about the cache memory and its organization. Now, next is the internal memory. In this I will talk about the semiconductor memories, the various types of the semiconductor memory, and memory chip organization, memory module organization. So, first look at the basic concept. As I discussed in previous lectures, that the data transfer between the processor and the memory that takes place through the two registers. Memory here, internal memory means the main memory or physical memory it is called as. So, the transfer of the data between the processor and the memory, the intermediary components which are there in the processor are the MAR register and the MBR register. MBR register also named as an MDR register. Memory speed is measured through access time, memory access time, and the memory cycle time. The difference between the access time and cycle time is basically both are time, basically time required. Access time is the time between placing the address by the processor and the data availability or the data provided by the respective module, the time difference between these two events, that is your access time. Cycle time is the minimum time delay that is required between the initiation of two successive memory operations, can be read operation or can be write operation. Memory cycle time is usually larger than the access time, because it also includes the recovery time between two successive read or write operation or any two operations. Some time gap is required to stable the memory, we can say. So, that is called as a recovery time. And for the semiconductor memories, this memory cycle time is usually range from 10 nanosecond to 100 nanoseconds. So, now look at how the main memory is accessed by the processor. What are the connections are there, what are the components are there at the processor side is required, and the relationship between the memory addressability, address space, and the processor registers. So, this is your processor. This is processor. Processor contains two registers. One is MAR. Apart from other register, these are the two register right now I am mentioning here, MAR and MBR. Then we know that processor connects to the main memory. Let me draw first the main memory block. This is main memory, and main memory have starting from 0 to 2 raised to the power k minus 1. So, total 2 raised to the power k locations are there. 2 raised to the power total k locations, that means address space is 2 raised to the power k. So, how many address bits are required? How many bits are required to address any location in this type, in this particular memory? K bits are required. So, address bits are k bits. Then each location, let us say, contain some n bits, and that is called as a addressability. If you multiply both the things, 2 raised to the power k into n, then it will give the total size of the memory. Now, the communication part. So, in the communication part, system bus is used. So, system bus have three parts, or the lines or wires are logically divided into three groups. One I am saying is address lines, this is data lines, and third is a control lines. So, the wires in the address bus are grouped into 3 and combinedly it is known as a system bus. System bus. Now, this address bus is connected, or MEA register is connected to the address bus. So, connection I am showing like this. MBR is connected to the data bus, and the control signal will go, let us say here control unit is there, CU, that is connected to the control lines that send the read signal or write signal according to as per the operation required. Now, memory is also connected. Memory will read through connection, read the address through the connection of address lines with address lines, and it also should be connected to the data bus as well, because whatever address is provided through that, suppose for example read operation, for the read operation data address will be accessed through the address lines, and the required data will be provided over the data lines. So, through the data lines MBR register is connected, and then it can be copied into the MBR register, and further it can be used inside the processor for the processing. Control lines connection is also required, that says read write operation, read or write or memory state or whatever. So, this is the typical connection between the memory and the processor. So, we have seen in the previous slide how the processor is connects to the main memory. Now, look at the various semiconductor memory types. What are the semiconductor memories are there? So, we have here I have categorized here in type, what category, whether it is a read write memory or it is a read only memory. Then what is the erasing method, how to erase the contents to copy the new contents, what is the write mechanism, how we can write it, and whether it is a volatile or non-volatile. So, first is the random access memory, RAM, comes under the semiconductor memory. It can be read as well as write, it is a read write memory, and the contents can be erased electrically at the byte level, byte by byte contents can be erased, and write mechanism is also electrically read and electrically write. So, it is a electrical memory. Volatile means once the power is switched off to the system, then the contents will lose. So, that means it is a volatile memory. So, contents will be loose when the power is switched off. Then second category in the semiconductor memory is the read only memories. Read only memories have the different have some variations, versions, variations I say. Variations means purely read only memory, or it is the programmable read only memory or erasable programmable read only memory, then electrically erasable programmable read only memory, and finally it is a flash memory. Flash memory and this PROM have similarity, the memory cell is mostly same, but slight difference is there that I will cover towards the end of this lecture. So, in a read only memory, as the name says that it is a read only memory, so though no erasing is possible and you cannot write. For programmable read only memory or electrically erasable read only memory, the content can be erased as well as you can write the new contents as well through the electrical method. So, erasing technology, it can be either using the ultraviolet light, chip level, complete chip can be erased, or in electrical erasable you can erase byte by byte, and some bytes can be erased and then can be written the new information. So, complete chip will not be waste. At the chip level means the whole contents you have to remove and the new contents you can put it. So, small corrections you cannot meet. And this memory, the read only memory, is used for the program, such programs which we always require and we do not want to be modified. Let us say BIOS program. So, BIOS program are written on the read only memory, basic input output system program, which requires each computer system. So, these programs or instructions are written in this memory, this type of memory. So, one advantage is because it is only read only memory, let us say it is BIOS is implemented usually through the ROM. So, there is no danger of the accidentally contents of this memory can be erased or can be accidentally also it can be erased, that possibility is also not there. And so, that is the one advantage. So, like system programs or BIOS basic input output programs, these sort of things, that instructions are usually fixed, not change frequently, because changing will be costly here if you are erasing and then writing again. So, that will be a costly step. So, most of that your contents are same, do not going to change frequently. In that case the ROM is the appropriate choice. And the another feature or the characteristics of this ROM is it is a non-volatile. Non-volatile means even the power is switched off, the contents will be retained, content will not be lost. So, let us start with the static RAM or random access memory. Why it is called as a random access memory? Because each location can be randomly accessed, or accessing any location will take a constant amount of time, whether it is a first location or it is a 1000th location in that memory. That is why it is called as a random access. So, static memories or static random access memories are memories that consist of circuits which capable of retaining their state as long as the power is applied. So, that is why it is a volatile memory. Bits are stored as on a on off switches, and switch, the behavior of the switch is get through the transistor. Transistor is basically a switching device. The construction of this memory or construction of one cell of this memory is a complex, requires 6 transistors. So, the cost per bit is more compared to we will see that in a dynamic memory which requires lesser number of transistors. So, cost is increased because the more transistors are required. So, the size will increase. So, this memory becomes expensive. So, let us look at the static RAM cell organization, how the cell is designed for SRAM memory. So, in this diagram you can see this is a one cell, it have total 6 transistors T1, T2, T3, T4, T5 and T6. 6 transistors are there and they are the CMOS transistor. You can see here this is a P type transistor. CMOS stand for complementary metallic oxide semiconductor. So, CMOS transistors are there, P type, and this is N type. N type transistor. So, PN 2 type transistors are there. So, it is a combination of P and PN here. So, that is why it is called as a complementary. One is positive, P for positive, N for negative. So, it is called as a complementary metallic oxide semiconductor transistors. The operating voltage is less. So, the power consumption is less in this. These transistors operate in 5 voltage, maximum 5 volt. So, that is why these transistors are better for implementing the SRAM. Now, memory is what? Memory is basically storing, one cell of memory can store 1 bit of information. So, 1 bit of information either it can be 0 or it can be 1. So, now through this circuit we need to represent 2 states, one state is state 1, another state is state 2. So, how the state 1 will be implemented? state 1 will be present. So, C1 is high, the C1 point is high. So, if for N type transistor, if I will give here high voltage I will give at this gate, then the transistor will be in a saturation state, means it is closed, the circuit is closed, means it will, the current will flow like this. So, the C1 is high. So, C1 high will make, and C1 high will make this as a connected. So, T2 your T2 transistor will be on, and T2 transistor will be on and T4 transistor will be off. So, this is off, this will not be connected. So, it is off, I am talking about the first state 1 right now, and this is on. C2 is low. So, C2 low means this is disconnected, disconnected means here low voltage will come, low means this T1 will be off. So, this is off and T3 will be on, because it is a P type. So, the condition for on and off for P and N type are reverse. So, here it is on, on means it is connected. So, here this is connected, so that is why the voltage will, current will flow, and this also connected, and at bit line B 1 will be, 1 information will be, or its state will be 1. And here address line, if the address line is active, then this 1 can be read or write as per the operation. For 0, the conditions will be reverse, C2 is high and C1 is low, and the set of transistor T2 and T3 will be off, and T1 and T4 is on. So, in that case this bit will be read, and this B bar means a 0 information will be read from here, read or write. So, this is the simple construction of a SRAM cell, and one cell can store 1 bit of information. And this memory is used for the cache memory, because it is access time is fast. So, it is used for cache memory. It is a costly. Why is costly? Because the number of transistors which require, and the density means amount of bit can be stored in a given unit area is less. Why? Because more transistors are required, so one cell will occupy more space. So, the number of cells which can put on a single silicon chip will be less. So, density is less, that is why cost is more, and more number of transistors are required. So, it is suitable because it is a faster. So, that is why it is suitable for the cache memory implementation. Now, look at the another type of memory cell, that is the dynamic memory. So, in the dynamic memory cell, you can see compared to the static memory cell, it is far simpler. Only one transistor is required and one capacitor is there. Here one capacitor and one transistor is there. So, and this is grounded, and here the bit line is there, and address will appear here. Address bit will appear here. So, the one line it is shown for 1 bit. Similarly, so 8 lines will be there. So, you can access the number of cells will be, these kind of cells will be arranged in a kind of array, and then it will form a larger memory. So, here in the dynamic RAM, why it is called as a dynamic? Because the charge due to this capacitor, as time progress, whatever charge is accumulated at the capacitor will be decayed. So, we need a refractory circuit to maintain that charge level, otherwise the information 1 can be 0. If the information state is 1, that state, if the charge due to charge leakage, that can become 0. So, to maintain that charge level, we need a refractory circuit. So, that is why it is a dynamic in that, means the, as far as the power supply is applied, the voltage level is not constant, not remains the constant. So, that is why it is a dynamic. In case of the static RAM, the voltage level, as far as the power supply is applied or power supply is there, the voltage level is remains same or constant. So, you do not require any refractory circuit there, but here it is not remain constant due to this capacitor charge decay problem. So, we need a refractory circuit such that the charge can maintain at that level. So, that in that sense it is called as a dynamic. So, bits are stored as charge in capacitors, charge leaks. So, we need a refreshing even when powered or power on. Simple construction compared to the SRAM, and because only one transistor is required and one capacitor is required. So, the size is small, density becomes more, cost per bit also will be less. When address line is active, bit can be read or written. If address line is not active, then in that case not active means this is disconnected and bit line no operation will be there. If address line is active, then whatever the charge is there, that will flow from transistor to. So, either transistor is disconnected or connected. So, disconnected means in that case it is charge is can observe here, and then accordingly the information can be treated as a 0 or 1. So, it is a slower operation. Why slower operation? Due to this capacitor. So, that is why it is good for main memory, because cache memory we cannot make as a cache memory is slow, because access time for the cache memory we want less, because the cache memory is something that processor access directly, or the most frequently used data we used to keep in the cache memory. The cache memory we cannot compromise with this. So, for the cache memory, because size is small, that is why to trade off between the performance and the cost, cache memories are designed with the help of static RAM and the main memories are designed with the help of dynamic RAM, because the main memory size is usually larger compared to the cache memory. So, to reduce the cost we use the dynamic RAM, but cache memory, that is why the cache memory size is small. So, we can use a faster memory or costly memory. Now, the memory is memory chip, how the memory chip is organized. One cell construction we have seen, whether it is a SRAM or DRAM. So, only the cell organization will be different, the other module organization or chip organization will remain same, whether I am using a DRAM cell or SRAM cell. So, as far as the organization is concerned, DRAM and SRAM is same functionality wise, only the difference will comes in terms of whether it is a how many cells I can put in a single chip, or whether it is in terms of the access time and performance wise. So, these cells, these individual cells are organized in the form of array, and each row of this array forms one word of the memory. So, this is the way how it is organized. So, you can see here in the diagram, the memory is organized in a array or cells of the memory. Each individual cell of the memory are organized in the cell in the form of array. So, in this array you can see total how many rows are there in this array. W0 to W15 total 16 rows are there, and how many columns are there? 1, 2, 3, B0 to B7 total 8 columns are there. So, it is a 16 into 8 bit memory is there. So, 16 rows and 8 columns. So, you can say the 16 words are there and each word contains 8 bit of information. So, to address this memory I need a device or a electronic device which is called as a decoder. So, the size of the decoder is I need a 4 cross 16 decoder. 4 inputs are there, 16 outputs, different combinations of 4 bits. First combination 0 0 0, second combination 0 0 1 up to all ones. So, total 16 combinations are there. So, the decoder is a device which gives me the different combinations of whatever the input whatever the number of input bits are there. So, in case it is 4 bits are sufficient. Why? Because 16 different unique location I want to identify. So, that is why it is a 4 cross 16 decoder is required. Now, each location. So, the location will be identified with these 4 address bits, and once let us say any combination 0 0 0 1 means the W1 will be accessed, and whatever information is stored at this cell, let us say here it is 1, maybe here it is 0, and this cell is also called as a flip flop. The combination of the transistor is such that it is a flip flop device, flip flop which can store a single bit of information. So, here let us say it is a 0 is there, here it is 0 is there, and other remaining 7 remaining how many has left, let us say 0 1 1 and let us say 1. So, how many 3 3 6 7 and one more I have to write, let us say 0. So, if this location is identified, then here at the output the corresponding bit will be observed here 0 0 1 0 1 1 0 1 and so on. Whether the operation is read or write, that is controlled through the RW control signal, read or write, and CS stand for the chip select. Whether the chip is select, if the chip select is 1, then this chip is can be operation can be done on this chip, whether it is a read operation or write operation. So, this is simple construction of 16 cross 8 bit memory. So, total 128 bit memory. Now, what is the important part? Important part is how many pins I required, because externally you will see your memory something, this chip is there and you have some pins are there that you have to connect to the rest of the system. You have to attach to your system such that this memory can be accessed by the other modules including processor. So, number of pins we look at, 4 address lines are required, 8 data output lines are required, 4 plus 8 12, 1 chip select and 1 read write, so 2, and power supply is also required. So, 1 for ground and 1 for power supply. So, total 8 for 12 16. So, 16 pins are required in this case to construct this small 16 into 8 bit memory. So, now let us construct a larger module of the or larger chip of the memory. So, now I am going to construct memory of 1K, 1 kilobyte memory, 1 kilobit memory. 1K cross 1 means 1 kilobit memory. So, in this organization you can see here the memory cells are organized in an array of 32 cross 32. So, 32 cross 32 means it is a 2 raised to the power total 10, 2 raised to the power 10 bits. Total cells are 2 raised to power and each cell can store 1 bit. So, it is a 2 raised to power 10 bits are there. How it is organized? In the form of row and column. Now, the address what will be the address size? So, 1K memory. So, address size will be 10 bits, 2 raised to the power 10. So, total 10 bits are required to, and these 10 bit address are divided into 2 groups. One group is the row address, 5 bit row address and 5 bit column address. So, row address will identify out of 32 rows, which one row will be identified through the row address, and from the column address out of 32 columns, one column will be identified. So, let us say this is the row and this is the column, which is one particular address represents this 1 bit. Now, here I am using one multiplexer 32 cross 1. Multiplexer is a device. Suppose let us say I give input to a multiplexer, 5 input to a multiplexer, or let us say in this case 32 inputs to a multiplexer. So, the combination of 2 raised to 5 and output will be always 1. Out of this 32 combination of 2 raised to the 5, one output will be transferred. One output will be transferred here. So, total 32 inputs will be there to this multiplexer and one will be transferred as an output out of these 32. So, here whatever is selected here, so this is enabled, so this will be transferred and that bit can be read here as an output, whether this bit is 0 or 1, whatever it is read for a read operation. If this control signal is read. For write operation, in place of the multiplexer, here it will be used demultiplexer. So, demultiplexer operation is the reverse to the multiplexer. Then chip select is there, one input. So, now look at, so this is how this memory 1 kilobit memory chip is designed. Now, how many external connections or pins required in this case? Address bits, total 10 address lines are there. So, 10 pins for address, 5 for column, 5 for row, 10, and 1 output pin 11, and 1 read write and chip select, because read write only 1 pin is required. Why? Because if it is, this signal is 1, then I can say is a read, if this signal is 0, then I can say it is a write. So, only 1 pin is sufficient. So, 1 read write and 1 chip select and 2 for the power, anyway it is required. So, a total 3 plus 2 5 is a 15. So, total 15 pins are required. So, for constructing 1 kilobit memory, we require 15 pins. So, for constructing 1 k bit of memory, we need 15 pins, and I also constructed a memory of 16 into 8, 128 bits only memory. That requires how many pins? If you remember, 16 pins it required for 128 bit memory. Here we construct a larger memory and number of pins are less. If the number of pins are less, that means definitely this is a good organization, because pins are less means the space it is going to be occupied, that will be less, space less, power consumption is less, cost, and that will reduce the cost. So, if the lesser number of pins are required, that memory organization is good. So, that kind of memory organization is called as a 1 bit per chip organization. Each chip is giving me 1 bit of information. Earlier 16 into 8 was giving me 8 bits per chip as an output. So, that is a 1 bit per chip organization is preferred over the multiple bit per chip organization. Now, let us discuss this particular chip organization is more detail. Let us say one memory chip one memory I have to memory chip I have to organize or design, that is 16 megabit chip, that can be organized as an 1 mega of 16 bit words, means 1m into 16. So, if 1m into 16, in this way I am organizing, then how many pins are required? 1m locations, rows, and 16 columns. So, 1m location means 2 raised to power 20. So, the 20 bit for the address part, 16 bit for the data output part. So, 20 plus 16 36 pins, plus 4 pins for the read write, chip select, and power, and 1 for ground. So, these both are called as a power only, power supply and the ground. So, combinedly known as a 2 pins. So, total 40 pins are required. Now, same size of the memory, I am organizing as 4K into 512 into 8. If you multiply all these things, you will get 16 megabit only. So, this organization says you have 4K total lines are there and 512 columns, each column contains 8 bit. So, for that how many pins are required? 29 pins for required for the data and the address part. Data 512 columns are there. So, 8 for the data part, 8 each column will give me 8, and the row address and column address will be 12 plus 9. So, 12 plus 9 is 21, 21 plus 8 is 29, plus 4 pins for the control pins, I can say, that always required for any kind of organization. Third kind of organization. So, third organization is I can organize the same amount of memory in 2048 into 2048 into 4 bit array. Again it is a 16 bit megabit memory. So, the cells are organized in an array of 2048 cross 2048, and each location, each column is giving me 4 bit. So, the row address and column address are 11 bit each. 2048 means 2k, 2k means 2 raised to power 11. So, 2 raised to power 11 means 11 bits are required. For row address, 11 bits are required for the column address. Now, to further optimize, this row address and column address can be multiplexed. Same address lines can be used for row as well as for representing the row address as well as for column address. If I can multiplex, let us say assume here I can multiplex, how to multiplex that I will show in the next slide, but let us say we could multiplex, then the number of pins will be half only 11 pins are required. One time it will represent the column address, one time it will represent the row address. Okay. So, 11 pins and then 4 pins for the data output, because each column is giving me 4 bit output. For each bit 1 pin will be required, and the 4 pins, that is the control pins, which is required. In this kind of organization, if I just add 1 pin extra, that will double the range of the memory which I can organize or which I can address. So, the total capacity will becomes 4 times. Range of row as well as range of column both will be double. So, the total capacity will be 4 times. Now, let us look at this organization, the organization which I am talking 2048 into 2048 into 4. So, in this organization you can see the memory array is 2048 into 2048 into 4. I have a row address decoder here that will decode out of 2048 lines or row, 1 row will be decoded. Now, how this address, column address and row address is multiplexed? Here we have the control signals are there, that is RAS, RAS stand for the row address selector, CAS stand for the column address selector. So, let me write row address selector. Similarly, column address selector, this is write enable. Okay. So, through the timing, first row address will appear, the lower 11 bit of your address part. Your address have total how many lines or how many bits in the address? 11 into 11, 22. Sorry, 11 plus 11, that is a 22. So, 22 lines are there. So, out of 22, first 11 bits will represent the row address, and the next group of 11 bits will represent the column address. So, first row address will appear, the row will be identified. Once this row is identified in cycle 1, let us say, in cycle 2 same lines are used for, now it will represent the next half of the address part. Your address part is 22 bits are there, 22 bits. So, the next half of address, the next 11 bits will now appear on the same lines. So, your address is appearing in a 2 halves, 2 times, one time only row address bits and the next time column address, or row and column is a logical. So, you can say in the first cycle only 11 bits of address is appearing, that will identify a row, and the next cycle next 11, once a row is identified, the next 11 bits will represent the column address. So, through the column address decoder the column will be identified. So, now this location is identified, and now this location have how many bits are there at this location? 4 bits are there. So, these 4 bits will be transferred here. This is the output buffer, and that is for read operation. For write operation, this data input buffer will be there, location will be identified in the same way, row first and then column, and then location is identified, and whatever the data is there in the buffer, that data will be written on these 4 bits of that location. That is just a reverse process of reading. Write process is reverse process of reading. So, the advantage of this is I am able to reduce the pins exactly half in terms of the addressing the memory, and the only disadvantage is that the row and column address, now complete address is identified in 2-step process. Half row address in one cycle or 1 or 2 cycle, depends upon the latency of the memory technology, and 1 or 2 cycles required for the column, identifying the column address. So, that delay will be there compared to if all 20 bits are going and all 20 bits are accessing the or identifying the location in a single cycle. If I have the same memory is 16 m into 1, if this same memory I can say 16 m into 1, in that case I have 20 plus 4. So, 24 pins are there and these 24 pins are accessing 1 bit of information, or it can be 4 m into 4 as well. 4 m into in the case of 4 m into 4, 4 m into 4 means each location is giving me 4 bit, total 4 m locations, and these 4 m location in a single cycle I am identifying these one location out of this 4 m location. So, I need a separate row address lines as well as the column address lines in this case to identify a location, but in the multiplexing process I am able to reduce the number of pins and that will reduce the size, cost. So, this organization gives better performance in terms of reducing the cost and in terms of the reducing the size of the memory module, and that will ultimately reduce the power dissipation as well, the amount of power which is required and amount of power which is dissipated. So, now look at the popular memory module. So, memory is basically, this is a chip organization we have seen. Now, these to make a larger size memory, these chips are placed in a groups, or these chips are placed on a one silicon chip, and the memory modules, are larger memory modules are constructed. So, the two popular modules which are commonly used in computers to design the computer memory is, one is a DIMM, DIMM, and one is a SIMM, SIMM. So, DIMM stands for the dual inline memory module and SIMM stand for the single inline memory module. So, the difference between, so here the picture which is shown to you, that is the SIMM memory module. SIMM memory module have the pin, all the pins at one side only, one side of the chip. So, the data path supported by this SIMM is 32 bit data path. So, total 72 pins are there. So, all the pins are one side only. So, out of 72 pins, 62 pins are used for the data and other pins are for other purpose. So, data part means 32 bit information can be at a time, can be flow from this memory for read operation or write operation. Another module is, that is a DIMM module. In a DIMM module, the data path supported by the DIMM module is 64 bits. So, larger data path means the amount of bit that can be read or write. So, this module supports 64 bit, and the pins are, this happened due to the pins are at both the sides, not only one side. So, that is why the data path support capability is improved. And these slots, you can see nowadays in the computers you have these kind of slot in which you can, in your motherboard you can place your memory, you can put your memory module. So, that is the DIMM slots. So, these slots are called as a DIMM slots. Now, as I talk about the memory module construction, so chip construction we know that how to make a chip, maybe it is a 1 bit per chip organization, or we can address and row address and column address can be multiplexed, or multiple bit per chip organization. Now, from this chip, one chip I have, one chip is constructed, and from this one chip how to make the larger module. So, we will see here with the help of 512 into 512 chip organization, 512 bit chip organization, single chip, how to construct a 256 kilobyte module. So, here I have 512 by 500 array of cells, array 512 into 512, and this is chip number 1. So, these many bits it gives. So, like that I used total 8 such chips. Each chip is giving me 1 bit information. How it will give 1 bit information? 9 bit of address, 9 bit of row address, 9 bit of column address. If you know multiplexing is there, in that case 9 plus 9 total 18 lines will be required. So, 9 bit row address and 9 bit column address, that will locate 1 bit of information, that 1 bit of information is go in this buffer. Similarly, all these, if the whatever address will appear, the corresponding lines of all the chips will give me 1 bit of information. So, for second chip will give me this, because this is 7th chip, okay, the 7th chip will give this information. Similarly, 8th chip also the same line, because the same address lines are given to all the chips. So, the corresponding lines and columns are located in each chip, and it will provide me 8 bit in a single read operation. And for a write operation, if 8 bits are provided, then as per the address information available here, these bits will be written in the each chip one by 1 bit per chip. So, that is a 256 kilobyte memory module organization with the help of 512 cross 512 chips. Total 8 chips are used. Now, with the help of this 256 kilobyte, now this 256 kilobyte one module is there. Now, from this 256 kilobyte module can be used to make the larger modules. So, can I make a 1 megabyte of memory with the help of 256 kilobyte one module? So, initially I started with a 512 into 512 bit one chip, and these kind of chips, 8 total chips are arranged such that it construct a 256 kilobyte one module. Now, this 256 kilobyte module can be used in a base module to make the larger size memory. So, how to construct this how to construct 1 megabyte of memory from or by using this 256 kilobyte of memory module. So, to construct this module, you can see here how many 256 is the my base module, 256 kilobyte is the base module. So, total, if I 4 modules, such 4 modules I am using, that will give me 1 megabyte of memory. So, from the 1 megabyte of, so 4 modules, this A, B, C and D are the 4 modules, A1, A2, A3, A4, A5, A6, A7, A8, that is giving me a 1 256K module. This is another 256K module, and this is another 256K module, and this is the last. So, I am adding 2 more bits, extra bits to, and the capacity is 4 times, you can see. From 256 multiplied by 4, 2 additional address bits are added, and these 2 bits 0 0, then this chip will be selected, or this module will be selected, 256K module. For 0 1, this module will be selected, for 1 0, this module will be selected, and for 1 1, this module will be selected. So, total 4 modules are there, and the within the 256K can be any memory location can be accessed with the help of 18 bits. So, the leftmost 2 bits of the address, if the 0 0, then I am accessing this module. If leftmost 2 bits of the address is 0 1, then this module will be accessed. So, first 256K byte will be here, second 256 kilobyte will be here, third 256 kilobyte will be here, and fourth 256 kilobyte will be accessed from here. Fourth means in the sequence. So, we start from the first 0 to total 1 megabyte, then this is the way how first 256K location will be here, and then next here, and next here, and next here, and each location will give me, as the into 256 kilobyte it is giving me 8 bits of the information. Now, the DRAM memory are basically which is used in computers, that is a synchronous DRAM. Synchronous means with respect to the processor clock it is synchronized. So, you can see in this diagram, so the access is synchronized with an external clock. So, you can see here the address appears, command is the read command, and after read command it takes 2 cycles, that is the latency you can see, and then it is producing 4 bytes of information. So, it is fixed that okay, after address appears, then 2 cycle latency will be there, and after 2 cycles it will provide the required data, and at a time how many data it, how much data it will give, 2 bytes or 4 bytes, that depends upon the data path and the memory organization as well. So, that means it is a synchronous DRAM, means synchronized with respect to the processor clock. So, what is the advantage of this kind of memory? The processor does not have to wait. Once address is appear on the address bus, processor knows after 2 cycles the data will be available. So, within that 2 cycles processor can do some other work. Other work means some ALU operation or some other transfer it can do, that does not require the system bus. Then the further development in the SDRAM is the DDR. In SDRAM you have seen that each cycle is giving me 1 byte of data. In DDR, in each cycle you can get 2 byte of data. So, that is why it is called as a dual data rate. So, how it is working? The clock appears, this is a row address selector. So, row address selector indicates okay, this is activated. So, means this row addresses appear on the address bus. Column address lines or column address lines are asserted, is a negative logic. So, that is why its assertion is in a negative voltage. So, as a column addresses appear. So, row address appears, in second cycle column addresses appear, 1 cycle latency is there, and then the data will appear, the valid data, each rising edge of the clock also 1 data appear, and falling edge of the data also 1, falling edge of the clock 1 data is appear. Compared to the synchronous DRAM, only SDRAM is there, 1 clock cycle gives only 1 data, but here in rising edge also as well as the falling edge we are getting 1 data in each case. So, the data rate is double here. So, the data transfer rate, that the rate at which the data can be accessed from the memory is now doubled. So, now look at the exercises for this lecture. So, one question is how memory organization impacts on the data transfer rate, how the memory organization can make difference in terms of the data transfer rate, that you have to answer. Second question is number of pins required or external connections required for 4 megabit memory chip if it is organized as a 4M cross 1, that is the first organization, and second organization is 1 M, M stand for the mega, cross 4 bits. So, now let us summarize what we did today. I talk about the semiconductor memory types, semiconductor memory types, the different semiconductor memory like RAM, ROM, the various version of the ROM, EROM, etc. And then I talk about the chip organization, from the chip organization, the module organization, how to construct a module, larger module, and we also seen the SRAM cell and DRAM cell organization, SRAM cell, DRAM cell. So, these are the things I discussed in this lecture. So, thank you very much, have a nice day.